Wow, today I shall be teaching you applications of integration, and we are going to be looking at area under the curve and application to kinematics. So we want to learn how to find area under the curve using integration. This is going to lead us to what we call definite integral. We want to find the area under the curve we are seeing on the screen between point B and A, which are called limits. A and B are called what? Limits. So we are going to be using integration to find area under the curve. That's our assignment today. And that can be connected to definite integral. When we say definite integral, we mean putting the limits b and a on our integral sign as we see on the screen. So this is definite integral and area under the curve. So let's look at some examples in finding the area under a curve. So I have the first example, integral s squared plus 2 dx between the limits 3 and 1. We can also call it boundary. Now we want to make a sketch of y equals to s squared plus 2, because we could be given the question in form of a diagram, okay, in form of a curve. You can see a Cartesian plane on the screen. I have the limits between 1 and 3. We have to find area under the curve between limits 1 and 3, and that's what we can also call boundary. What did I call it? We can call it boundary. Good, very fine. Now we want to integrate that function we have on the screen now. By integrating, that between those limits shows we are finding area under the curve. This is one of the applications of integration. So if I integrate that, I have x raised to power 3 over 3, then plus 2x. We all can integrate a constant. Now remember I told you that we must always add our arbitrary constant c. But for this case, we may choose not to write our constant, because we are going to be finding the difference between substituting 3 and 1. So the c will cancel out eventually. So we may not necessarily write our c this case. Remember I told you that while we were doing indefinite integral, that means without the limits. I hope you remember that. But this case, we are not going to put the c. We want to substitute the limits 3 and 1 now. So what do? We substitute 3 first in that result that we have integrated, and we find the difference between the two. Now if I put 3, that will be 3 raised to power 3 over 3 plus 2 times 3 minus 1 raised to power 3 all over 3 plus 2 times 1. So we have substituted 3 and 1. So that will give us, when we simplify what we have, we add and subtract, we're going to be having our answer. And I believe every one of us can solve this. 38 over 3 units squared. Because it is area, we have to put the right unit squared, or we say square unit. Now let's look at this example. We have 3s squared plus root x dx between the limits 4 and 1. You can see 4 at the top of the integral and 1 at the bottom of the integral. So we want to also find area under this curve by integrating one by one. So if I integrate that, I have 3x raised to power 3 all over 3. Remember, you add 1 to power and divide by the result. Plus, and I can write my root x as x raised to power half. If I add 1 to half at the top, I have 3 over 2. You divide it by the same result of your power, 3 over 2. So if we can now simplify further, we see that that 3 that we have there and the 3 at the top, 3 will cancel 3. The 3 is going to cancel 3, so we are going to have x raised to power 3. Okay, so let's see. The 3 cancels 3, so that gives us x raised to power 3. Good. X raised to power 3 plus, now if we put that correctly, the 3 over 2 at the bottom will become 2 over 3. x raised to power 3 over 2. Then let's put our limit 4 and 1. So the next step, like the last one we did, is substitute 4 in that result minus substitute 1. Then we find the difference. If I put 4 raised to power 3 plus 2 over 3 times x, that's 4 raised to power 3 over 2. Then we substitute 1 now. 1 raised to power 3 plus 2 over 3 times 1 raised to power 3 over 2. So if we simplify what we have in each of the brackets, it's going to give us our final answer, which I believe everyone can do in this class, isn't it? So our final answer is 202 over 3 units squared. Now let's look at this very one. We see two expressions in brackets. So the first thing we are going to do, we do what? We are going to do expansion. Let's expand those two things, expressions we have in the bracket. So we give us a quadratic function, as we can see on the screen, between the limit 2 and 0. So if I integrate the first term there, I add 1 to the 2, x raised to the power 3 over 3. I add 1 to the power there, 3x squared over 2 plus 2x. We are not adding our constant, as I've said, between the limits 2 and 0. Good. 2 and 0. So as usual, what do we do next? We substitute, isn't it? We're going to be substituting. So let's substitute 2 first. Let's substitute 2. Then let's close the bracket. Then we substitute 0 now. Let's substitute 0 in the same result as we can see the way I'm solving it. Substitute 0 to represent x. So if we simplify the two answers we have in the bracket, we'll get our final answer, which is 38 over 3 units squared. So we've been able to solve this question. You can try this too, isn't it? You will find it very easy to be sure you have understood what I've shown you. Good. We've done area under the curve. I hope you found it very interesting. Very good. So I think we need to proceed to kinematics. Kinematics. We're going to be understanding what kinematic is first before we proceed. Application to kinematics. We can apply integration to kinematics as well. What is kinematics? That should be the first question that we should ask. A very good student should ask, what is kinematics? Kinematics is an aspect of mechanics. Kinematics is an aspect of mechanics that deals with motion of particles, objects, and system of group of objects without considering what causes the motion, which is force. We all know that it is force that causes motion, isn't it? So force causes motion. So when we don't talk about force and talk about motion, then we are dealing with the aspects of mechanics that we call kinematics. Now let's look at these concepts which we have learned from this differentiation. Velocity v is the s dt. S is distance. Velocity is the s dt. Good. And acceleration is dv dt. I hope you remember this. And we can also write acceleration in terms of s, which is equal to the 2s over dt squared. Good. So if we still remember this velocity and acceleration as have just stated, then we can proceed. Let my ds dt be f of t. Remember, ds dt is what? Velocity. So if I integrate the s dt now, it's going to give me s distance. You remember, integration is what? Anti-differentiation. Okay, so if I integrate, I will get the original thing I differentiated. So if I integrate ds dt, I have s, which is f of t dt. So all we are saying is if I integrate the s dt, I have s. Then you will always add your plus c, which is arbitrary constant for integration. Now let's look at that of acceleration. Let our acceleration be dv dt, which is g of t. If I integrate that dv dt, I have a velocity, I have a v. Okay, so and that will give us gt plus c. Good. Let's look at an example. So take note of what I just told you now. When you integrate dv ds dt, you will get s. When you integrate dv dt, you get velocity. Good. So we have this question on the board. Good. A particle is projected in a straight line from a point O with a speed of 6 meters per second. At time t seconds later, its acceleration is 1 plus 2t meter per second square. For the time when t is equal to 4, calculate its velocity after 3 seconds. Then 2 is distance from O when momentarily at rest. So let's look at the solution, or let's prefer solution to that question. Good. Let v be the velocity after t seconds. Now, dv dt from the question is 2t minus 3. Do you remember? As I told you that acceleration is dv dt. Okay, so we are given acceleration as 2t minus 3 meter per second. That's why I'm representing it here with dv dt. Now, if I integrate that dv dt now, it's going to give me v. V will be integral of 2t minus 3 dt. If I integrate 2t, remember, if I add 2 to that power of 1 on t, if I add 1 to that power of 1 on the t, I will have 2t squared over 2. So if 2 cancel 2, I have t squared. Then if I integrate 3, I have 3t. So t squared minus 3t plus c. Let's put our constant as c1 here, because we are still going to have another arbitrary constant. So we call that one later c2, just to differentiate between the two constants. So if I integrate 2t minus 3, I have t squared minus 3t plus c1. Now, the initial condition, when t equals to 0, velocity is 2 meters per second. We are told in the question that initial velocity is 2 meters per second. So that means when the time was 0, at the very beginning, the particle was moving at 2 meters per second. So we use that as a condition to obtain our c. So my v is 2 now, equals to time is 0 minus 0. I'm substituting 0 in that t squared minus 3t plus c1. So t is 0 minus 0 plus c1. So from there, c1 is 2. So put your c1 as 2 now in that equation of v. So my v is t squared minus 3t, t squared minus 3t plus 2. And the question said after 3 seconds, calculate velocity after 3 seconds. Because it's velocity after 3 seconds, then I substitute my 3 in that v now. 3 squared will give me 9. Minus 3 times 3 will give me minus 9 plus 2. Okay, so the answer is going to be 2 meter per second if you substitute, or if you simplify correctly, 2 meter per second. So we have given solution to question A. Let's look at B. I hope we have clearly understood what the A part of this question is talking about. Now let's look at the B aspect. It said we should calculate its distance from O when it's momentarily at rest. When the particle is momentarily at rest, it means velocity is 0 at that point. There's a moment when the particle is at rest, velocity is 0. That's the interpretation. Good. That's the first thing we need to do. So we already have t squared minus 3t plus 2 for our velocity. So it means that's why we are putting equals to 0. So if I factorize that, t minus 1, t minus 2 in bracket, that's what I will have. So that means at time t equals to 1 or time t equals to 2, at the point when the particle is momentarily at rest, is at rest at time t equals to 1 seconds, and it's also at rest at time t equals to 2. Good. Let's conclude. Remember, we are talking about distance. Distance, I can get it from the s dt. From the expression I have before, the equation I have before, my ds dt is t squared minus 3t plus 2. So if I integrate the ds dt, it's going to give me my distance. You know, ds dt is v, and that's what we are seeing on the screen. Don't forget, the s dt is what? V, and that's what I've quoted it as t squared minus 3t plus 2. So if I integrate that, t squared, t3 over 3, minus, if I integrate 3t, add 1 to the power and divide by the result, 3t squared over 2 plus 2t. Of course, we know that the t that we have beside the 2 is t raised power 0. So if I add 1 to that 0, I will divide by 1. So I have 2t plus arbitrary constant c2. So we need to make use of this condition to get the value of our c. When t is 0, distance is 0. Because at point O, no motion has started. The particle has not moved at all. So distance is also 0. Because that's what they ask us to find. Is distance from O. When the distance is 0, then that time is also 0. So if we substitute in this equation of S now, our C2 is going to be 0. So if we substitute back that, so what do you think we're going to have? So we'll have us substituting when t equals to 1. It was at that point we have the object momentarily at rest. When t equals to 1, let's substitute it to get the distance. So if I put 1 in that equation, I have what I have on the screen. So my answer is 5 over 6 meters. Then if I substitute the other one, when t equals to 2, okay, when t is 2, and I substitute in that same equation of S that is at the top of the screen, I have 2 over 3 meters. So this brings us to the end of this example on kinematics. I hope you enjoy the class. Make sure you practice more questions and attend to the questions we have in our module for this course. Thank you.